we already know how to solve constant coefficient homogeneous FOLSDEs if the coefficient matrix is non-defective. What we're going to talk about now is how to handle the defective case. And this video has a subtitle, which is the polynomial times exponential ansatz. Now, unless you speak German, that word ansatz will be new to you. We'll talk about it in a minute. Before we get into how do we solve the defective case, let's remind ourselves for how to solve the non-defective case. Well, what do? There's two approaches. One approach is to use the matrix exponential, compute e to the at. To do that, you have to find the eigenvalues and eigenvectors. That really just helps you diagonalize. The matrix exponential is easy to compute. And your solution is just that matrix exponential times any old initial value you want. That's one approach. The other approach also requires finding the eigenvalues and eigenvectors of the matrix. You can see that both of these approaches really require us to have a non-defective matrix. In the first approach, in order for this matrix v1 through vn to be invertible, so you need all of those eigenvectors, which means your matrix has to be non-defective. In the second approach, if you want to get a full solution set, which we know is going to be n-dimensional, we need n linearly independent eigenvectors. So these both fail pretty dramatically if A is defective. Let's figure out what to do by thinking about one particular example of a defective matrix. So here is a constant coefficient homogeneous FOLSDE, and of course we know any such vector equation can be converted into a system of scalar equations. Let's just go ahead and try our approach for the non-defective case and see what happens on this matrix. The first step is to find the eigenvalues, which you do by computing the characteristic polynomial. In this case, we have one eigenvalue with algebraic multiplicity 2. Let's go ahead and find the eigenvectors, which we do by computing a minus lambda I, row reducing so that we can find the null space. You can see here that the rank of the row reduced form, which means the rank of the original matrix, is 1, which means there is a one-dimensional null space, happens to be spanned by the vector 1, 3. We've just discovered that our algebraic multiplicity of this eigenvalue 3 is 2, but its geometric multiplicity is 1. Since we only have one eigenvalue and one eigenvector to work with, you might say, okay, what are our solutions? They should just be e to that eigenvalue t times that eigenvector, right? Great. Pause the video and check that this is actually a solution. But it's not the whole solution, because we know there should be two linearly independent solutions, and we only found one. So we're in the market for another solution. I want us to think back now about single Constant-Coefficients. This e to the 3t times something should remind us of the solution to d minus 3y equals 0. Well, what happens if you have d minus 3 squared y equals 0? Your e to the 3t will still be a solution, but we need another solution, and that solution comes from multiplying e to the 3t times t. What about d minus 3 cubed? We need three solutions, and we obtain them by multiplying first by t and then by t squared. If we have a higher order equation, of course, we need a polynomial of degree k, the same order as the equation. That's just sort of a thing that occurred to us. What we're going to do now is check and see, maybe the same sort of trick will work. What we're doing is called making an ansatz. Now, ansatz is the German word for making a statement before. What do we mean in that case? We mean make a guess about what the answer is going to look like, and then use that guess to find an actual solution. In this case, the ansatz we're going to make is that our other solution x2 should look like v2, that is some other vector, plus t times v1, the eigenvector we already found, times e to the 3t. And you can see that's very much like what our solutions to the various powers of d minus 3y equals 0 look like. Each time you multiply each previous solution by t, and then you have to add another one because we expect one more. Okay, let's see if we can do it. To apply an ansatz, we're going to assume that our solution has a particular form, and we're going to work out what v1 and v2 have to be. So let's compute the two sides of the equation we want to solve and see what we get. We just apply the fact that A is linear, and then remember v1 was supposed to be an eigenvector for A. Now on the left-hand side, we just have to differentiate. We have to use the product rule because there's two t dependencies here. Having algebraically cleaned that up, if we look at the left side and the right side, we notice there's some stuff in common. There are two terms that involve a t, so we can subtract that term from both sides. We've also got an e to the 3t on both sides. I'm going to go ahead and put the v1s on one side and the v2s on the other. And because we're dealing with eigenvalues, somehow in the background of all of this, I'm going to rewrite that as a minus 3i applied to v2. So you can see, well, if we want a v2 that will make this work, v2 had better satisfy a minus 3i v2 equals v1. Can we find such a vector v2? And I think the answer is yes, of course we can. We're pros at solving linear equations. Let's go ahead and do it. Now this is a non-homogeneous vector equation, so we have to use an augmented matrix. But other than that, it's exactly the same approach. Minus 3 times the first component of v2 plus the second component of v2 has to equal 1. Let's just pick a value for x1. We end up with 1, 4. That's v2. So let's go ahead and write down what our solution is supposed to be. Remembering that x1 is e to the 3t times 1, 3, and our formula for x2 is e to the 3t times v2 plus tv1. We obtain that formula, or if you like, we could write it out. And there we have two solutions, x1 and x2. I will let you check whether those two are linearly independent, but the answer is yes, they are.